Hello students, welcome to the next lecture on segmentation. We looked at several segmentation techniques in the previous lectures. We looked at thresholding, region grooving, mean shift based segmentation, and then k-means clustering based segmentation. Especially when you take segmentation techniques like thresholding and region grooving, we saw that the segmentation regions are not actually constrained by the length of the boundary. So today in this section we want to add this boundary length as an optimization scheme to come up with very powerful new segmentation techniques. So first one that we are going to look at is the so-called intelligent scissors or lazy snap. Now this one is available in popular image processing, photo processing software as well. So in GIMP it is this tool that's called scissors select tool. I think in Photoshop it's called magnetic lasso tool. So you can see when you try to segment with this, you click one point, and when you click the next point, it clings onto the image boundaries. Can you see that? It usually clings onto the image boundaries. You see? So yeah, sometimes it makes mistakes. So, but usually it clings onto the boundaries. So you can see that. So with a few number of clicks, you are able to segment out the image using these kind of tools. So how is this done? So you can see the line that is drawn when I click clings onto image boundaries. That means if you consider the cost along the line, it must be less for image boundaries or the high contrast pixels, or the pixels at which the gradient is high. So this is what we are going to look on to when we come up with this algorithm, and we'll understand how to implement that also. So in this, first we will look at the Dijkstra's algorithm based intelligent scissors, and then later on we will look at active contours that also works on the image gradients. So this diagram is an illustration of what I did on GIMP. You click the mouse at a point on the image boundary, and then when you move the mouse, let's say the mouse pointer is here right now. So then you will notice that the line from the mouse clicked point, that is the seed, to the mouse right now will follow path, and it will usually cling onto the image boundary. Next, what you do is you click here again. Then once again it will cling on to the image boundary and reach the mouse where it is right now. So with a few clicks you can complete this segmentation. So here you can see it will cling on to points where the image gradient is high. Okay, so how to find a path from seed to the mouse that follows object boundary as close as possible? So the answer is define a path that stays close as possible to the edges. So we know that the edges are characterized by points with high image gradient. So you can see grad IP, the gradient magnitude of the image. Some positive inverse measure of the gradient is what we want to assign to node costs. So in this case we will look at node costs. Later on we will go for link costs when we actually implement this. So right now think about these node costs. Now every pixel has a cost. So if I ask you to start from the seed and find the least cost path to where the mouse is right now, here, can you do that? I think as a human being you can quickly find a path, but what we want to do is to automatically find that least cost path. So like so. this least cost path. Okay, so how do you find that path? So it is common to define the weights directly on edges of the graph grid and use the Dijkstra's shortest path algorithm rather than working on these nodes. Okay, so what we assume right now is that there are directed edges WPQ between two pixels P and Q with 8 neighborhood connection. So you can see this pixel with intensity 11 has the 8 neighbors. This, and these links have costs. Okay, so one more thing about defining these link costs is they must be rotation invariant. Now assume that each of these along this line the cost is 2 per unit. Okay, 2, 2, 2, 2 and so on, and therefore 2 times 7 you have 14 as a cost. But if you rotate the image, now you can see you would not have 7 2's. Now you have 1, 2, 3, 4, 5 2's. That means the cost is only 10. So what must you do? What happened? Because now the distance between two points, 2 units along which we compute the cost along that line has increased. So as a result, we must multiply that by square root of 2 to get 14. So we have to scale the gradient measure by the length of the edge. Okay, now let's define this. So now you can see we have a node P for every pixel, node P. So you can see that node here, and link between every adjacent pixel E, P, Q. So E is an edge and Q is this other adjacent pixel. So we have to define WE, the cost of that link. Note, each link has a cost. This is different from the first example where each node had a cost. Okay, so we want to hug the two image edges. So how to find cost of a link from pixel intensities? So actually now when we consider this link, the red link between P and Q, you can say this pixel is quite dark, right? This pixel is quite bright. Therefore, perpendicular to that edge, our gradient is quite high. So if we take an inverse measure of the positive gradient magnitude, then you can get that line to cling onto the image boundaries. So the link should follow the intensity edge, and we want intensity to change rapidly perpendicular to the link. The cost of the edge should be small when the difference of intensity perpendicular to the link is large. Okay, so now we can define kernels or windows to calculate these edges for the horizontal edges, vertical edges, and diagonal edges. Okay, let's first take the E2, a horizontal edge. So we can consider the 4 pixels around that edge, this pixel, this pixel, this pixel, and this pixel, to compute the gradient, because that seems to be the sensible thing to do. Okay, so we can have 1, 1, -1, and -1 as the weights. So if you apply that, you know that you get the gradient actually using the central difference formula. But since we are applying the central difference formula twice, here as well as here, so you can see we are using length between here and here is 1, length between here and here is 1. So we have to actually divide it by 2, but since we are using 2 of them, length between this and this is 1, length between this and this is 1, hence 1 over 4 in front of the kernel. So that is okay. So the length of the edge here is 1, the length of this edge is 1. That's okay, so you don't have any other multiplier. So now let's consider this one. Okay, so how do we compute the gradient? The difference here is square root of 2, so you divide it by square root of 2, and you have -1 here and +1 there, +1 there. Okay, so now we know how to compute this gradient. So what you know that this is the gradient computation formula. You move perpendicular to this direction, and then Okay, so how do you get that positive inverse measure of the gradient? So you can uh, put that into some kind of a Gaussian function like this and then obtain a value. Or otherwise you can use the previous formula that you saw, so 25 over 1 plus the magnitude of gradient. So this is valuable, assigning low penalty to large directional derivatives and large penalty to small derivatives, because this property, so you can see if you have a small gradient that should not be cut and then you have a large weight for that, but if your gradient is large then you assign a small weight to that. So this is also good. Okay, so we saw last time in the previous slides that we need to multiply by the length of the edge. So here in this case the length of the edge is square root of 2, so therefore you have to multiply by that value. Okay, so the cost of an edge in this case is this one, and for the whole path we add that up. So when we actually run the least cost path, you can see the path will try to shrink as much as possible. Shrink means it will try to follow the least cost points. The least cost points are actually the image edges, so that's why this path clings onto the image edges when you finally run Dijkstra's on them. Okay, this same thing is shown in a continuous domain like this. Okay, so now let's look at how this algorithm runs. This is what you need if you want to get this implemented. So I may give an assignment for you to do to have this implemented. It's very nice actually. Okay, now let's consider the initial seed point. The cost is 0 and the 8 neighbors around. So for each of these ones we assign infinite cost. So at the initial infinite cost. So each of them are infinite. So init node costs distances to infinity. Set p seed point cost to 0. So this is what we are doing. Infinity, so infinities to as infinities. Okay. Right. So assume that we have the link costs computed using the previous knowledge that we got. For each, expand p as follows. For each of p's neighbors q that are not expanded, so that means you have to have these lists when you run the algorithm. So we'll briefly look at those lists again. Set the cost of q, this is the important formula, set the cost of q as a minimum of cost of p plus cpq, that's the link cost, over cost of q. Okay, now let's consider this one. So what is cost of q? That's infinity. What is cost of p? 0. What is cpq? 9. So you can see now this infinity gets replaced by 9. You can clearly see that. So in the same token, for every single node in this stage, the cost gets replaced by the link costs. And then what we need to do is, if q's cost change, make q point back to p. So you can see we have these arrowheads pointing back to the c. So these arrowheads we would use eventually to get back to the seed when the mouse moves around, to draw the path back to the seed. Okay, then put key on the active list. So you can see the active list, key on the active list. Actually p we remove from the active list. Now in the active list right now there are 8 nodes. All the red nodes are on the active list right now. So set R node with the minimum cost on the active list. So the minimum cost on the active list is this node with cost 1. Okay, so what's the cost here? It's still infinity. This one is infinity, and this one is also infinity. So what we need to do now is to run this once again on this node with 1. So let's take this one. So we have to see whether it's infinity, cost of q is infinity, cost of p is 1, cpq is 3. So you can see definitely this will become 4. and we have to point the arrow like that. And now let's consider this. So in this case, you can see Q has the cost 4. Q has the cost 4, and CPQ is 2, P is 1. So actually 1 plus 2 is 3, which is less than 4. So this will become 3, and this we cut and we point the arrow like this. So you can see as it expands, we know how to go along the least cost path to the seed point, which is circled in blue. So I think now you understand the algorithm. If you know how to find the link costs and then run this algorithm, you have the segmentation. Then after that, it is just a displaying activity. Okay, so I'll give you a little bit time to see whether these are correct. Okay. Alright, there you go. Once again, you have the seed and the mouse pointer. From the seed, we keep on expanding, and we have the process nodes and the active nodes, and the active node with the least cost. From the active node with the least cost, which is this one, we expand like so, and then we pick we make that processed, and then pick the least cost one, and expand along that also, right? And then we go there, and then you see from B to A there are these arrows pointing. So there is only one path like that. So along that path you can follow. So you can see when you click at A, that means when you insert a seed, it will take some time for you to run the Dijkstra's algorithm. But after you run the Dijkstra's algorithm, from any point B in the grid, finding the path back to A is instantaneous. It's constant time. You just have to follow the arrows. So therefore, that's why after clicking, it's extremely fast to move the mouse around. Okay, so these are the properties of this Dijkstra's shortened path algorithm. It computes a minimum cost path for the seed to every node in the graph. This set of minimum paths is represented as a tree. So running time with n pixels is O(n) squared. If you use a priority queue, it's big O n log n, so you must use a priority queue. It takes less than a second for a typical image. Once this tree is computed once, we can extract the optimal path for any point to the seed in constant time. Not actually constant time, I'm sorry, linear time, not constant time. It runs in real time as the mouse moves. What happens when the user specifies a new seed? Then it will once again have to run the Dijkstra's algorithm. So a correction finding the path back is linear time, not constant time. I made a mistake there. Okay, so there are many extensions of this directed graph, restricted search space, different edge weight functions, and multi-resolution processing. We will not deal with those things now. So with this you can do nice things, place someone else's face on top of that. That's all. Okay, so thank you.